So welcome to the second lecture of our Van Hoon series, lecture 2025. Briefly to mention, as Professor Leclerc mentioned yesterday, so Van Hoon endowment for the department is actually a very unique opportunity for our students and also faculty across the universities, especially young faculties like us, me and Professor Im, that we have the opportunity to connect and interact with esteemed scientists in our field. And on that regard, Professor Andrew Rappe, who is a professor at the Chemistry and Material Science Department in the University of Pennsylvania, has actually done quite a remarkable things, but I would just briefly explain one of my personal experience. So we did not have much interaction personally, but one of his work in 2017, which basically motivates me to kind of think a new research direction. That is basically I'm focusing now, which possibly he will discuss a bit today. So basically photo-induced change in ferroelectric response. So that's basically one of my research motivation from his fundamental works. So without further ado, I'd like to welcome Professor Andrew Rappe for his talk on spontaneous symmetry breaking. Thank you.
Well, thank you so much. It's really a great joy to be here. Now I've met even more of you, and I'm really appreciating the depth and breadth and quality of research that goes on here and the wonderful people who make it happen. So thank you for hosting me. It's been a great time so far. So yes, today I want to talk about spontaneous symmetry breaking. So for those of you who study ferroelectric ceramics or ferroelectric single crystals, this will be a little bit of review for you. But for those of you who study metals, you know, phase transitions are very important in metals, but we're not accustomed to them being easily reversible after the material is made. And so that's where I think you'll be pleasantly surprised. I like to say that ferroelectrics are hard materials with a soft degree of freedom. So they're hard in many respects, but they have one particular very compliant way they can respond. And so, you know, we material scientists, if there's an interesting fundamental phenomenon, we say, how can we use it for some new material applications? And so the ferroelectrics already have widespread use, as I will tell you, but there are lots of new ways we can envision a next generation of ferroelectrics. And so I'm going to tell you about some of the fundamental science that underlies these and how it relates to applications. Okay. So the first part of this talk, I will be discussing a classic problem that we've made some contributions to the understanding, and this will be our springboard for understanding new ferroelectrics, is to understand the most prototypical ferroelectric, the perovskite oxides. Okay, so here is a motivational picture. So some of you may look at this and you see grain boundaries. But what I want to tell you, we'll discuss the symmetry breaking in a moment. Basically, because of the spontaneous symmetry breaking, you get a very special category of grain boundaries. Yes, you have one crystallite and another one, but they're related. Their energies are exactly the same. The interface is, in some sense, not permanent and can be removed. And so we refer to these as ferroelectric domain walls. You can think of them as twin boundaries. And so then this is a little bit more of an atomistic picture. I think it may be a little bit hard to see. So the color kind of follows the direction of the arrows. So the arrows in this red region are pointing to the right. And in the blue region, I think they're pointing up. So we have some 90-degree domain walls, meaning the direction of the polarization is different in the different regions. Okay. So what we have, the perovskite crystal structure, we introduced it yesterday in the context of the hybrid halide perovskites. We have atoms that like to live in an octahedral cage of anions. And so in this example, it's titanium with 6 oxygens around it. But then every octahedron is corner shared to its neighbors. And then we have the A cations, just like we talked about yesterday. So this is the classic perovskite structure. But what I like to say is, you can calculate from database searching what is the preferred bond length between titanium and oxygen. And what is the preferred bond length between lead and oxygen? And if that ratio of bond lengths happened to be exactly square root of 2 to 1, then both bonds would be happy. But no set of atoms actually provides this perfect ratio. So because perovskites are a multi-component material, they're AbO3, you almost always see some distortion away from the perfect cubic structure. And the amazing thing is that you can access this cubic structure. It's not so high energy that you can't get a cubic material, but then at lower temperatures, the distorted structures are preferred. And what I'm illustrating here is that this titanium atom could shift downward or it could shift upward. And those two distortions, by symmetry, are exactly the same energy, exactly the same properties. They would have the same vibrational frequency, same everything. But the orientation in space is going to turn out to matter, as we'll see later. So what we like to do is we like to make an energy diagram where the cubic crystal is here with zero polarization, and then either polar structure being pulled up or pulled down, the same energy. So we refer to this as a double well potential. But in fact, life is more complicated than this, and for things I won't show too much today, it doesn't only have to go up or down. It's a cubic structure. It could go left, it could go right, it could go forward, it could go back. There's actually 6 equal energy minima for this cubic structure, and this is just the tetragonal phase. You could also have an orthorhombic phase. You could have a rhombohedral phase. And so there's lots and lots of opportunities, all starting from what we think of as a pretty simple cubic structure. So this is what I mean by spontaneous symmetry breaking. And I've already labeled these as 0 and 1. So I'd like you to think of the idea that you could have an up polarized region and it would stay that way. And you have a down polarized region, it would stay that way. Those could in principle be memory bits, and they could be non-volatile, but they could also be switchable. And this is something that's already in use. Ferroelectric RAM is a known technology. People purchase them and use them. Various devices make use of ferroelectrics as memory elements. And as I will be saying more as the talk proceeds, there are new ways of thinking about ferroelectrics in the computer context. But I'm already showing you some interesting, more complicated emergent patterns that can evolve. So you don't just have to think of it as an up region and a down region. Take a look here. So this is a polar up and this is polar down, and then the boundary could be this domain wall, but it doesn't just have to be vertical. This one has some stair steps. And then here is a more complicated picture where you have some 90-degree domain walls. So it's polarized to the left, it's polarized down, and all the regions have different polarization. And then you can have hierarchical polarization domains. Can you see that there's a pink region? And then there's a yellow region. So these alternating stripes are different polarization. But then if you actually zoom in within these yellow stripes, there's domains of other polarization alternating here. So it makes multiple levels of polarization reorientation complexity. And you might say, well, why does that happen? And the easy answer is strain compensation. Okay? If you have a crystal that could be cubic, but it actually could then elongate in one direction and shorten in another, that's a great way to relieve strain. And so then if the system has to more and more gently compensate for strain, it can make big decisions and then smaller micro decisions within those. So that's kind of the high-level answer for why you get this. And then there's an even cooler thing. I'm not 100% you can convince that you can see this. So we're labeling this as vortex. So can you see that there's like a dark region here, and then there's a tan region, but within that, there are spins that go around kind of in ovals. If you want, after the lecture, you can come up and see from my computer. People are referring to these as polar skyrmions or polar vortices. And basically, you can think about it this way. The dipoles just want to be left alone to do their thing, and they would like to all point the same way. But it's not favorable for all of them to point the same way because it brings a lot of charge to the surface. So you might think it'll be up and then down. And so between the up and the down, they actually have a region that goes sideways. And so they wind up making circular patterns. And these, it's thought that those have special properties, not the main point of my remarks, but I think it's a very beautiful offshoot of some of the ferroelectric things I'm going to say today. So ferroelectrics already have many applications. So they are used for computer memory storage. I think I just mentioned that to you. This is an actual ferroelectric RAM module. It's certainly used for ultrasound imaging. So a major use of ferroelectrics. So this is the hierarchy of smart material properties. That everything in the world is dielectric, okay? Then only a subset of dielectrics are piezoelectric, meaning if you apply an electric field, the system changes its shape. And then within the piezoelectric, some of them are pyroelectric, meaning if you change the temperature, you will get a changing polarization across the material. And then finally, the most exclusive category is the ferroelectrics. So for something to be ferroelectric, we insist that you can have a permanent polarization one way, but you could apply an electric field and reverse it. If the material is so polar that you can't reverse it with an electric field, we don't call that ferroelectric. And we should be able to access that high symmetry phase that I talked about at the beginning. If the material melts before it goes nonpolar, we don't call that ferroelectric either. We just call it pyroelectric. So ferroelectrics are a very special category. And so what I just foreshadowed is the communication between these dipoles, these off-centering of individual atoms and other things such as strain is what gives them their power and their properties. Okay. So we will come back to this. So this is just a glimpse at some of the smart material properties that can be related to each other in this family of materials. So I mentioned piezoelectricity. So you can see here, suppose you apply an electric field and you get a strain, or you apply mechanical stress and you get a polarization. So we would refer to that as a piezoelectric connection between electrical and mechanical properties. Then I referred to piezoelectricity. So if you heat the material, you change the polarization, or if you apply an electric field, you can change the entropy. So these materials can be referred to as electrocaloric or pyroelectric. And then finally, you can connect the mechanical and thermal properties as well. In principle, you could apply a strain, change the entropy, or apply a temperature and get a strain. Okay. So the point is, we'd like to build up an understanding from the smallest scale to the largest scale to be able to understand ferroelectric materials and make materials design innovations, suggest new materials, new ways of thinking about materials, and therefore new applications. Okay, so if you make one of these broken symmetry systems, the dipoles don't really know where to go. And so this is kind of a good caricature of what it might look like when someone like my friend Alp makes a ferroelectric material. At the beginning, the dipoles go in all different directions. So to organize them, we apply an electric field. Electric field is conjugate to the polarization. So if you apply an electric field, you'll start from 0, 0, and you'll make the material more and more polar as you orient the dipoles. And then if you take the electric field away, the polarization will go down, but just a little bit. And this is a stable state. This is like the up state or the 1 bit. Then if you apply an electric field the opposite way, you can eventually convince the dipoles to go the other way. And then if you release the electric field, you get to a different state. You see that? If you apply the electric field up and take it away, apply the electric field down and take it away, the structure of your material depends on what's the last thing you did to it. So we refer to that as hysteresis. The state of the material depends on what happened to it before. And that's very important for this memory application. That's the whole logic of it. You could apply an electric field up, store an up bit, down, down bit. Okay. And what's happening at the smaller scale, you apply an electric field, those domain walls that I just presented to you, the boundary between up and down, somehow they're moving until you maybe take over the whole material and you've polarized it. Okay, so to understand ferroelectrics, we need to understand these domain walls. We need to understand the properties of the individual up or down phases. And we need to understand what is the effect of defects. Because as all of us know in the material science department, no material is perfect. And so we need to think about those things. Okay, so here is our basket of techniques. Of course, You might like to say, well, just do the most accurate job that you can. You can model every electron in the system and get a really accurate quantum mechanical result. But that is the most accurate and the most costly. So then it turns out density functional theory is an amazing compromise. You can model much bigger systems pretty accurately. But we'd love to go to something where we approximate the quantum mechanics, or where we don't use quantum mechanics at all and use the classical interatomic potential. And so why would we like to do that? We would like to start by using first principles calculations to tell us what our force field should look like. And then we're going to wind up with an accurate and efficient modeling procedure. Okay, so we're going from Schrodinger's world, where we study quantum mechanics, which is mostly limited to zero temperature properties. We don't have external fields. And then here we go to a classical world where the ions move according to Newton's law, right? Just F equals ma. And we can predict emergent properties in mesoscale materials in the computer. This is a powerful thing to be able to do. And having a force field is crucial for this. So I will just show you briefly how we do this. I'm curious, before I put this up, how many of you have heard of I.D. Brown and the idea of bond valence? Is this something that has come across your radar? A couple people. Okay. Well, this used to be a really important thing, that if you did X-ray diffraction, you would say, I think the atoms are here. You know, I have a solution for the structure. But does it make sense according to bonding? Are the bond lengths and bond strengths even reasonable? You would use this kind of bond valence approach. And so my friend Peter Davies taught me how this bond valence works, and we actually use it as an energetic criterion. It's now the core of our molecular dynamics. So it's kind of getting a second life. Okay, so the idea is that every atom has a preferred atomic valence. Like oxygen wants 2 bonds, right? Titanium wants 4 bonds, and lead wants 2 bonds. So in lead titanium. Okay. Now we can calculate the actual atomic valence, and then we will say there's a force on the atoms as they try to get their preferred valence. So look at this example in water. When the water is at its ground state structure, we'll say that's 1 bond and that's 1 bond. So oxygen has a valence of 2, hydrogen has a valence of 1. But now if I shorten this bond too much, its bond valence goes up. You might say, well, that's great, more bonding. No, in this world, hydrogen doesn't want more than 1 bond. So that's too much. So there would be a force moving the hydrogen away, moving the oxygen away, so that their valences could go back to the preferred value. That's it. So it's a very simple idea. Okay. And then, so the one thing we've added in the last, decade or so is the idea that sometimes an atom prefers that its bonds aren't symmetrical. You see, if the bonds were this way, the vector sum of 1 bond and another bond would be 0. If the bonds are like this, the vector sum is not 0. The resultant vector is down like this. And so what we find is that for water, that's preferred. So we would add one more term that we call the bond valence vector term. So that's turns out that makes these interatomic potentials better. So I hope you look at this and you're not instantly, motivated to run for the hills. I'm hoping this looks not too complicated to you. That of course the atoms have charges, so we have Coulomb's law. We have short-range repulsion, so no atoms really overlap each other. Then we have this bond valence thing. Every atom's valence is supposed to equal the valence it's supposed to have. And then we have this bond valence vector. And that's it. That's the whole potential. Okay? And so it's very simple, and we can fit it rather easily. And we've done this for many perovskites. And then we can model millions of atoms. And so now I'll show you how this works. Okay? So we want to know how domain walls move. It turns out people thought they knew how domain walls moved long before we ever came around. But they made some assumptions that turned out to be wrong. Okay. So this is the classic model that the domain walls move according to what's called Mertz's law. This is an experimental observation, that the higher the electric field is, the faster the walls move. But then people needed an understanding what happens. So you have your up domain and your down domain, but you're trying to take over one more plane of dipoles. Are you all familiar with the idea of nucleation and growth? That when you have any transformation, it doesn't make sense for all of them to flip at the same time. they'd all be crossing the barrier at the same time. It's too high energy. So you need a nucleus and then a few more flip and a few more. So we're going to do nucleation and growth. So, but this classic theory suggests that the nucleus would be a large, sharp triangle. And the idea is if you're starting to pop out another plane of up dipoles, some of them are going to be head to head, and they're not going to like that because there's lots of Coulomb repulsion between the red guys and the yellow guys. So they worked out a theory where they could fit Mertz's law based on this idea of this triangular nucleus. But then other friends of mine came along and calculated the energy of the domain wall using density functional theory. But if you put in realistic energies for the domain wall, you get that the critical nucleus has to be huge. Has to be 50 angstroms high, 40 angstroms wide. So the activation energy is an EV&a. So domain wall motion will be incredibly slow, too slow, not what's observed experimentally. And so this was brought to my attention by my good friend Yiwei Chen, who knew there was this classic model, and then the first principles basically made it invalid. So we started to look at this. Okay, so the general idea of nucleation and growth, this is just a picture to show you what I was saying. You have a down domain and up domain, then you pop out a little region, it probably grows fast along the electric field direction, then it widens, and then you've taken over one more plane. And then you repeat the process. But how does that happen? Okay, so the other thing to know about nucleation and growth is the nucleus feels a lower energy because of aligning with the electric field, and that's represented as this parabola. You see the area of the nucleus is stabilizing, but the perimeter is what costs you that domain wall energy. And so if you add this linear term and this quadratic term, here, you can find what's the point at which the energy is maximized, and after that, the nucleus is actually favored to grow. So that's the type of model we want to develop. And so to do that, we do a multi-scale modeling approach. We did density functional theory, and actually just using 8-unit cells was enough to sample all kinds of distorted structures, fit that bond valence that I told you about, and then we could do molecular dynamics. Oh, I say here 25,000 unit cells. Yeah, we actually went up to over 1 million unit cells. Okay, it's a very efficient model. So we can see things happen as a function of time. We can apply real electric fields. We can change the temperature, and then we can see the growth. And so people sometimes like to see a graph like this. This is how well our classical simple bond valence model reproduces density functional energies for about 2,000 structures. And so we're very happy with this. The agreement is great. Okay. So are you ready? Here's what we're doing. We have a down domain. So this is all our modeling cell. We have a whole bunch of down planes, a whole bunch of up planes. The only plane we care about is the one plane that's about to be taken over. You see it's blue, and now it's about to become red. Okay, so now let's see if I can run this. Okay, here. Can you see those arrows wiggling around? That's just thermal fluctuations. But there is an electric field, so if enough of a fluctuation aligns with the electric field, it might stay. Oh, did you see a couple of them flipped? Here, you see down here? Oh, but they already went away. Here, a couple of them flipped. Can you see that? Now, can you see that more of them are flipped? You see that? We're not telling it what to do. All it knows from us is Newton's law. You see, we're not saying, why don't you make a domain and here's a good idea. We don't tell it anything like that. But look what it's doing. It's elongating really rapidly, and now it's widening. Do you see it's doing nucleation and growth? It's so smart. And so what I would say is this is a computational experiment. So we can now harvest data from our experiment and say, okay, what really happened? Okay, so if we look back at the movie, at the beginning the dipoles were random, but they were all pointing down. Then something happened, then something else happened, and in a couple of picoseconds, this plane was flipped. Okay, yes, we use a pretty big, here we go. We use a pretty big electric field because we can make things happen faster, and computer time is at a premium. Okay, so what we can do is gather statistics. We can do this flipping experiment lots of times and get rates. So the first rate is, how long does it take to make a critical nucleus, you see? And you say, well, how do you know if it's a critical nucleus? We look at it, And if it survives, it's beyond the critical nucleus. If it is destroyed, it's too small to be the critical nucleus. We look for nucleus sizes that have a 50% chance of living. That's the critical nucleus. And so we can find how fast do those form. Then
We assume periodic boundary conditions?
we assume periodic boundary conditions. But if we have 50 planes, then what happens between this one and this one will not be influenced by the next domain wall. Yeah, so we have to.
I was wondering how you deal with
Oh, yeah, we don't want to have lots of boundaries. Yes, for sure. So it's an infinite crystal, but it just happens to be periodically repeating. Yes. So we calculate all these rates. So for example, if you're looking along the electric field direction and two friends have already flipped, this is going to be one of the fastest ones. This one, where you go sideways and none of your friends have flipped, that's going to be one of the slowest ones. So we tabulate all these rates, and then we can do a Monte Carlo model, which lets us model much larger area much more quickly. And so now you can see it's kind of gray as a layer fills in, and then you'll see a darker gray as the next layer fills in, and so on. And what you're seeing up in the upper left is the first layer flips, but by the time the first layer is partly flipped, the next one flips, and they all make these beautiful sigmoidal patterns as a function of time. So we can then calculate domain wall velocities, essentially from first principles. First principles to MD to Monte Carlo, and we get the speed. And it agrees really well with some experimental reports of the domain wall velocities, and so we feel quite encouraged. But in my mind, okay, that's good. We get like quasi-quantitative agreement with the experiments. But the important thing is what we learn. What does the critical nucleus look like? This is a side view of the critical nucleus. Do you remember we popped out a little square region and then it got longer? So the critical nucleus is like a 3x3 square. But what I would direct your attention to is this is the domain wall, and then it cuts the corner. You see? So this guy doesn't have to lose all his polarization. This guy doesn't have to lose all his polarization. So it becomes beveled, and that's less domain wall than actually going straight and straight. Next, do you see that this arrow is smaller than this one or this one? So the polarization can become diffuse, and that reduces the energy as well. And so these are the concepts that make the critical nucleus as low energy as it is, and that explains why the velocity is a lot faster than people thought.
Is the polarization smaller than the segments longer? So this is kinking, you get a longer boundary, right? Compared to the straight one.
Both of those effects add to each other. The domain wall is shorter. See, this would have been 1, 2, but instead it's only square root of 2. So it's less domain wall, and this polarization is smaller than bulk, but it's larger than it would have been if it was right on the domain wall, which is 0. So it recovers some of its polarization, and the actual domain wall is shorter. Yeah, there's less interface area. Okay, so just to summarize this first part, how am I doing here? Okay, summarize this first part, you can see our critical nucleus is only 3 unit cells by 3 unit cells. I was saying the other one was like 15 unit cells by 10 unit cells, something like that. And so our critical barrier is 2/10 of an electron volt. Whereas if you take Miller-Weinreich and then you plug in the density functional theory domain energy, you get 1.6. So we now can rationalize the experiments by saying, instead of a sharp triangular nucleus, you have a diffuse beveled square nucleus, and it can be much smaller in size. So this is a completely new model, and it explains the polarization well. Okay, so then we had some friends of ours say, okay, that's for domain wall motion with no defects. But we're pretty convinced we always have defects, and defects are the most important thing, okay? Now, we do always have defects, but we weren't sure how important the defects are. So on the left is what my friends would say. You see, you have the domain wall, it moves until it gets to a defect. Then can you see how it's stuck? Like the rest of it made progress, but there's a defect here, there's a defect there. So they're all getting stuck on the defects. Why do they say that? Because if you apply a small electric field, the velocity is slow, and it keeps being slow, and it goes up exponentially. That means you have creep. And so you're getting over some barrier. Then in this white region, you're in the process of getting past those barriers. And then at high electric field, you have flow because the pinning isn't strong enough anymore. Okay, so that's the model of defect motion. Does that make sense? So we went and looked at this, and we actually used as a test subject not the 180-degree domain wall, but the 90-degree. And I'll show you what we found. Okay, so we did molecular dynamics on these guys, even larger unit cells, but we were doing 90-degree domain walls. You can see the polarization is down and to the right and down. So these are, but it's kind of universal. Okay, and so here are our velocities. Do you see all these data here? These are for different temperatures. All of these curves have to go through 0, 0. So you can, but we can't access this because it just takes too long. So they all start slowly and then swoop up and then bend over and become linear at larger fields. Do you see that? So our data have creep at low electric fields, and then depinning, and then flow. But the one thing we forgot is we didn't include any defects. Okay? We get this from the intrinsic material. Okay? So I think that's pretty cool. So now I want to just tell you why. And I'll make that as brief as I can. So you see our nucleus is kind of a square shape, which I showed you before. And so this was the Miller-Weinreich model. I'm not going to go through all of this math, but I would love to go over this with anyone who's sort of like super motivated by this separately. But basically the ratio, they had this like large aspect ratio, and it's because you have the wall energy and the depolarization energy. These guys were convinced that the electric field, due to the charges at the head-to-head domain wall, were the most important thing. And so, but what I showed you, do you remember what we learned from our first study? The dipoles are smaller at the boundary. And the amount of domain wall area is reduced. It's only about 40% of what you'd have because you have square root of 2 instead of 2. And you have enhanced dielectric constant at the boundary. And so for all of these reasons, that makes the aspect ratio go back to 1 to 1. And so, yeah, so you have an enhanced dielectric constant, and the depolarization energy is 1 over the dielectric constant. So that reduces the depolarization energy. And then you have smaller boundary charge. The polarization being reduced reduces the depolarization energy. And then they left out the cancellation effect. Remember their triangle? There has to be another triangle. It can't just end. And the two make electric fields that are opposite to each other. So that reduces the depolarization by a factor of 2. That also reduces the depolarization energy. So when you're all done, this is the depolarization energy if you took Miller-Weinreich at their word. And then if you say, oh, but it's actually beveled, you get here. Oh, it's beveled and the dielectric constant is higher, you get here. Beveled and dielectric constant is higher. And you have the forward part and the backward part of the diamond, and then you have the reduced polarization in the region right near the domain wall. And look, it cuts it down by almost 3 orders of magnitude, okay? And so that's how you return to the regime where the square nucleus makes sense. Okay, so how does that explain creep, depinning, and flow? Are you ready? Do you remember this little inverted parabola I showed you? That the energy is as a parabolic based on the area that aligns with the electric field, but it's a linear cost of the amount of domain wall area. So it should have this shape, and if you just take a derivative of this simple energy, you get that the critical nucleus length is 1 over the electric field. So the critical nucleus length would look like this. So now suppose you run an experiment at low electric field. Here you'd have a big nucleus, you see? Then if you increase the electric field a little bit, the nucleus goes down in size. Does that make sense? And a smaller nucleus you can form much faster. But now suppose you're already at high electric field. You have an extremely small critical nucleus. Now you increase the electric field, the nucleus almost can't get any smaller because it's so small. You see? So you don't get that extra bang for your buck. The electric field being bigger, of course, helps the speed. But by reducing the critical nucleus, it's an exponential influence on the rate. And so for small electric fields, you have a region where the critical nucleus is shrinking, and then it bends over in the place where the critical nucleus is almost constant. So these are the ways that we think about ferroelectric switching, especially There's probably an influence of defects, but it's not the dramatic reason why the velocity versus electric field looks the way it does. So that's the first thing I wanted to tell you. Okay, the second thing I was hoping to get to is what happens when you have strong disorder and this kind of spontaneous symmetry breaking. So in other words, we said you're supposed to have equivalent up and down. But what if there's something in there that's scrambling the dipoles? What is the resultant behavior? Okay, so it turns out the reason we like to look at relaxor ferroelectrics is they're extremely useful materials. And so I'll tell you about that first. Okay, so this lower right panel is the dielectric constant as a function of temperature for a material that's basically a normal ferroelectric. Do you see the dielectric constant is rather low, and then it shoots up and it shoots back down? That is so narrow. You really can't engineer a device to stay in that narrow range. So using that as a high dielectric is very tricky. But if you look at these materials with greater doping, what you can see here is the dielectric constant goes up and then it comes down, and there's a bunch of different responses. Can you see it almost looks like it's a shaded region? These are saying, let's apply the electric field, measure the dielectric constant with different frequencies. I could oscillate the electric field quickly or slowly, and you get different results. So that means some of the dipoles are responding fast, some of the dipoles are responding slow, some are responding ultra slow. So you get a different result depending on the frequency, and the width of this peak becomes a lot wider. You see it becomes 100 Kelvin or more up at a dielectric constant of 20,000. So that's a high dielectric that you could imagine using if you have a 100 Kelvin window for operating. So relaxor ferroelectrics are very useful materials. Like one area that they have a huge application is as piezoelectrics. So you apply an electric field, they make a huge response. The polarization changes and the strain of the material changes. So anyone who has gotten an ultrasound recently has encountered this material or one very similar to it, lead, magnesium, niobium oxide plus lead titanate. So in the first part of the talk, I was mostly talking about ferroelectrics like this. Now we mix 3 different cations. Look at this. We mix magnesium 2+, niobium 5+, titanium 4+. But it's still a perfect crystal. It's all perovskite. But when you visit, you say, oh, it's +5, +4, +5, +2, +5, +5. And so the dipoles don't know what to do. You see, they're very much influenced by these variations in charges. So the dipole alignment is not as orderly. And so the phase transition behavior is not as orderly. And that is what is being illustrated here. The disorder makes it dipoles in different regions respond differently, and that makes the response more interesting. Okay, there are 3 transition temperatures. I will only say a little bit about this. If you're at high enough temperature, this is when you're in the ferroelectric phase. This is 1 over the dielectric constant. So the dielectric constant goes up, it's almost linear. And if you extrapolate here, you would think you go to 0. But the dielectric constant actually turns around. The place where the actual data deviate from this line, that's called the Burns temperature. So that's kind of the most famous way of characterizing relaxor ferroelectrics. It's by finding their Burns temperature. If you do what's called acoustic spectroscopy, you can detect that there's another temperature at which something happens, which is T star. And then finally, you get what's called a freezing temperature. You can fit this not to an Arrhenius law, but you can recognize an almost Arrhenius law, e to the minus energy divided by kBT. But the temperature is how far you deviate from this. You need a finite temperature here. So it's like it freezes at some finite temperature and nothing else really happens. So these relaxers have very interesting dynamics. Okay, so this is what people used to say about relaxers. Maybe I shouldn't do this way, but I like to show you what I think is the wrong way, so then you'll sort of get the update. People would say, well, at high temperatures, the dipoles all respond individually. So it acts like a regular dielectric. Then you start to cool down, a few of the dipoles pair up, you get what they would call polar nanoregions in a nonpolar matrix. And so part of it responds fast, part of it responds slow, and these nanoregions get bigger and bigger until they gradually freeze. Okay, so much of this I think we've been able to show is not 100% right, and it's sort of an interesting story of how it becomes modified. Okay. Okay, lots I could say, but I'm just going to say a subset of these things. Okay, so again, we did molecular dynamics. Now we developed that same kind of model, but you could imagine fitting it so it deals properly with lead, magnesium, niobium, titanium, oxygen. A little more complicated, but it actually worked out really well, better than I would have thought. And so we have the same kind of model. We just have parameters for the different cations. And you can see the fitting again is quite good for all of these things. Okay. So we have a lot of analytical tools, which I would love to tell you more about, but I just really sort of want to teach you the most important thing, because I have a couple other stories that I want to tell you today. But when you do a molecular dynamics study, like I'm saying, you have a window into what's really happening. So you can use a lot of different analytical approaches. So the simplest one is to say, let's look at the fluctuating leads. Okay, remember, these B cations, these are all different. This could be a niobium, this could be a titanium, this could be a magnesium, who knows? But all the A cations are still leads. So we say, let's look at the lead off-centering. Just keep life simple, okay? And now we say, what direction are you going? What direction are you going? And we say for close ones, for far ones, for really far ones. If it's a regular ferroelectric, wouldn't you think they're all displaced parallel? Does that make sense? That's kind of like our expectation. So all we care about is not even the size. It turns out all the dipoles are almost the same size. We care about the angle. We say, you're moving this way, you're moving this way. That's an angle of 70 degrees. You're moving this way, you're moving this way. That's a 120, okay? So we make a histogram of the angles. We'll call it a pair correlation function. We'll write an integral, but it's just tabulating. What angles do you have? And does it make sense that if the whole thing is uncorrelated, that the angle should be 90 degrees? Because it could be parallel, it could be anti-parallel, it could be anything in between. So 90 is the expectation when there's no interesting dipole dynamics. But then if they start to correlate, it would head towards 0. Do you get that? Okay. Let's see some real data. Here we ran simulations of relaxor ferroelectrics at a whole bunch of temperatures. Okay, can you see here at 100 Kelvin, do you see it's essentially like at 90, and then it maybe tips down to 89. So that's pretty much, it's above the Curie temperature, it's not a ferroelectric at all. Then we cool it. This is kind of cool. Look, it's almost 90, but it actually trends down almost to 80. So they're saying, I see you. I have a little bit of interest in what you are doing. But an average of 80 degrees, that's very gentle association. They're just like distant acquaintances. Now we cool it down a little more. See, we go from 500 to 400. And look what happens. We have like 70 degrees, and then look, 60 trending down to 55. Are you guys seeing all this? Okay. So this is quite a bit more correlated than 80 or 90, but now as we cool down, look what happens. This part goes to 50 and 40 and 30. But out here, they all stay the same. Do you see that? So the dipoles are getting, maybe 30 degrees. That's kind of like a reasonable dielectric with some scattering, okay? And then, but once you go 8 nanometers, all bets are off. That means there's a domain wall between those things. If you're 8 nanometers apart, forget it. You're actually in a different domain. So what this tells you, can you see the guide for the eye of the blue and the red? The domain size does not change with temperature. The data are telling us it's an 8 nanometer domain size, and you get more and more correlated within your domain. But outside the domain, all bets are off at all temperatures. You see? So that is a huge difference from the conventional wisdom. And what we find is all the dipoles are participating in one domain or another. There is not a nonpolar matrix. All the dipoles want to be doing something. They're just making different domains. Okay, so here is our view. At the highest temperatures, we more or less agree that you have individual dipoles are not really correlated. And we make an analogy. This is sort of like steam, right? Each water molecule has a dipole, but they don't really correlate. Then you cool down through this Burns temperature, and we can find domains. We can look for dipoles that have some direction in common, and they're gently aligning. But then if you look at a later time, down here, do you see we have a time axis? So this is one snapshot, and this is some later time. Some of the domains have disappeared. Some have merged into two, and other domains are reoriented. So this is what is referred to as the dynamic relaxor phase. And then we cool down some more past this T star, and what you find is that you can definitely identify domains, and they don't change that much. Some of them have reoriented, like this guy starts to point towards us, and this one is almost the same as it was before. So this phase where the local dipole clusters, the nanodomains, reorient rapidly and break and reform, we say this is similar to hydrogen bonded water. That all the waters are in dipoles, they're all hydrogen bonded, but the hydrogen bonded network breaks and reforms all the time. So then we go to what's called the static relaxor phase, and we liken this to slush water. So slush is, when you have, there's been a snow, and then there's some ice coexisting with some water, and so some of the dipoles are more stuck together, and some are more free, all at the same time. And so there's a lot of kind of reorientation of small ice particles, I guess I'll say. And so then finally, when you have the frozen phase, the dipole directions of the nanodomains do not evolve much with time, and the nanodomains themselves do not break and reform, and we would say this is pretty much like ice. So this is our analogy. In other venues, I've sort of looked in more detail at the analogy between relaxor ferroelectrics and water. That's something that we could discuss separately. But basically, this model of relaxor ferroelectrics answers a lot of questions about why relaxors behave the way they do, and it has provided a platform for designing new materials that have signature relaxor properties. Okay, so with the time I have left, I want to tell you about a consequence of spontaneous symmetry breaking that relates to the optical and electronic properties. In particular, how it leads to an unusual kind of photovoltaic effect. And it's referred to as the bulk photovoltaic effect. So first I'll teach you what that is, and I'll say why I think it's interesting and promising for future applications. Okay. Okay, so we're really at a very interesting time where the acceptance of photovoltaic technology has ramped up quite rapidly over the past few years. It used to be that it was a tiny portion of our electricity generation and that around the world. But due to economies of scale and reduced pricing for conventional solar panels, acceptance is growing. There are tax incentives in some jurisdictions, but it also has just dropped in price. And so the idea of using photovoltaics as a next generation energy alternative is becoming a reality. What I'd like to show you here is that one of the promising ways to look at what I want to tell you about is this is how conventional solar cells are made. You need to create two different materials and interface them. So in a silicon solar cell, this would be P-type and N-type materials that make a PN junction. And when you do that, the carriers cross over at the interface and you get a trapped electric field. And this is what sorts out the carriers, right? That the holes can only move one way, the electrons can only move one way. When you have a polymer solar cell, you have what's called a bulk heterojunction. And so similarly, electrons and holes separate at those boundaries and are transported in the hole and electron transporting materials. What if there were a single material where you could shine light on that material and carriers just knew which way to go? Holes went one way and electrons went the other way, just by the properties of that material. So that's what's being illustrated conceptually on the right here. Wouldn't that be a nice thing? It would be a much simpler fabrication process. And so that is what is offered by the bulk photovoltaic effect. So we're contrasting that with the idea of an interfacial photovoltaic effect. Okay. Okay, so actually this is not a new area. The seminal experiments revealing that this is possible were done starting in the late 1960s. And this is a textbook from 1980 by my good friend Vladimir Friedkin that is a seminal work in the field. You know, already a lot was known about bulk photovoltaics, and that's now 45 years ago, right? So what is new and exciting is the notion that we can use materials design of ferroelectrics with bulk photovoltaics. In other words, bulk photovoltaic effect, can we find it in new material platforms? So I'll tell you what was known about in the early days and then what the new generation can open up for us. Okay, so basically, like I'm saying, you can find publications about the bulk photovoltaic effect going back to the 60s, and that phrase was used even as early as the 70s. But you can see there are like 3 or 4 or 5 publications per year. But now we're up above 1,000 citations and more than, oh my gosh, this is an old graph. There's probably about 500 publications a year that relate to bulk photovoltaic effect. So it's really a field with a lot of growth. For the physicists among us, the bulk photovoltaic effect, its physical expression relates closely to concepts of quantum geometry and topological physics. And but for those of us in a more materials frame of mind, it's an interesting alternative way to separate electrons and holes. And that's what I'll be focusing on, but I certainly want to teach you the physical principles first. Okay, so there are 2 major mechanisms of the bulk photovoltaic effect. One is referred to as shift current, and one is referred to as ballistic current. Okay, so when you have shift current, here, okay, so this is a cartoon of an electronic band structure. Is that something that you're familiar with seeing? That you have a crystal, you can find the electronic states? So then if you shine light, you could take an electron from a state here and excite it up to the conduction band. Now, if you look at a long enough time, you'll only make excitations that conserve energy. But for very short times, you create a coherence. All the states start to become excited, and for a brief moment in time, you create a wave packet. So that's why I'm drawing this gray oval here. You sort of make a linear combination of all these states, and that's a wave packet that moves in real space. Now you might say, well, what about minus K? It turns out that if you break inversion symmetry in the crystal, the wave packet at K and the wave packet at minus K do not move in equal and opposite directions. And so you can get a current from this transient wave packet effect. It's a pure quantum effect. The electrons are not moving in an electric field or anything like that. So I think this is very interesting. And the other effect is the idea of, we call it ballistic current. So again, we go back to the same kind of band structure. So if you have an electron, you excite it at K, and then you excite at minus K. But now suppose you have phonons. So they scatter the electron from K to K prime, and from minus K to minus K prime. There's no reason the phonons have to scatter at the same rate. And can you see I used a very small arrow and a very big arrow? So that means I would get a larger population here than I would there. And so the 2 populations wouldn't cancel and you get a current from that. So these are 2 important mechanisms. There's actually others, but we'll focus on these for today. Okay, so there are a bunch of people, friends of mine, who have made very interesting contributions to understanding shift current. So I'll show you the physical expression, but basically you can grab onto it by saying, okay, the response function, how much current I get, is the intensity of transitions, like how many transitions happen per unit second, and how much current I get per transition. So it's just kind of a product of these 2 things. So these are referred to as dipole matrix elements. This is referred to as the shift vector. So we look at these 2 quantities. And basically, if we can calculate this shift current, now we can start to do materials design based on it. So a lot of interesting things have been happening recently. This is an experiment by friends of mine where they measured the shift current, or they measured at least the bulk photovoltaic current, and then they compress the material. And what they see is that one component of the photovoltaic response doesn't change as a function of stress, and another one is dramatically enhanced by a factor of 4 just by compressing the material. You change the atomic structure, you change the bulk photovoltaic effect. Another one, Marin Alexei has called the flexophotovoltaic effect. So if you bend a material with a tip, you're locally deforming it. You change the way these band structure looks locally, and so you get different excitations, you get different scattering rates, and you can get a different photovoltaic effect whether you deform the material or not. And then finally, you can change the photovoltaic effect with temperature based on different availability of the phonons. Okay, so I'm going to kind of skip through a couple of these things here. Okay, so this is an early study of how we can affect this bulk photovoltaic effect. So we come back to the perovskite structure. So this is kind of linking first part of the talk on ferroelectrics to the idea of bulk photovoltaic effect, which resides in inversion symmetry broken materials. So suppose we take an alloy of lead titanate and lead nickel oxide. So I write it this way because if you write lead nickel O3, nickel doesn't love to be +4. So we'll assume that there's an oxygen vacancy somewhere nearby the nickel. And so actually, this nickel plus vacancy offers visible light absorption. So that's what makes this, if you could say, photoferroelectric, an optically active, an optically absorbing in the visible ferroelectric. But then we could make this structure with any number of layers of lead titanate per layer of lead nickel oxide. And it turns out the amount of shift current changes dramatically. This is the 2 layers. So it's 1 and 1, and then this is the 6 layers. So the pink one is over here, and the black one is over here. And what you can see is they have the black one you get almost no photocurrent, and the pink one you get a ton of photocurrent. And that's very surprising to me, because the nickel layer is the one that allows for the absorption of visible light. But now I only have that as 1/6 of the material. Somehow you get a lot more current that way. You see, so these are the kinds of mysteries that being able to calculate something new, like predicting the shift current from first principles, allows us to do materials design, but we're still getting surprises. And so developing an understanding of why this is, in a way, we need to do materials design in momentum space. You see, we think about rearranging the bonds or rearranging the local environment of an atom. But instead, we're moving that intensity and shift vector, and we're increasing the bulk photovoltaic effect that way. So you're moving atoms in real space, but you're rearranging the response function in K space. So that's kind of an interesting thought, I think. I think in the interests of time, we're pretty much out of time, yeah? So why don't I just go to my acknowledgements, and then we can have some questions and answers. Okay, so for the first part of the talk, you can see that this was really pioneered by Ilya Greenberg, and then some extremely important work by Shi Liu, Hiroyuki Takanaka, and Younghan Shin. Then for the relaxor part, again, Ilya and Hiroyuki, with important work done by Yubo Chi and Chihao Zhang. And then the bulk photovoltaic effect was led and started by Steve Young, with Ilya and Aaron Schenkler and Zhenbang Dai, Lingyuan Gao, Ban Zhang. And it's a pleasure to acknowledge my main experimental collaborators in some of this work, Lane Martin, John Spanier, Iwei Chen, Peter Davies, Takeshi Agami, and James LeBeau. And for support, much of this work was supported by the ONR over the years, as well as the Department of Energy for an extended period of time, and more recently through the Army Research Lab. And with that, I will wrap up, and I'll be happy to take your questions. And thank you so much.
Okay, who's going first? Any question? Okay, Frank.
I'm interested in how you constrained the molecular dynamic simulations by the bond valence principle. And I want to understand whether this is a generally accepted method or whether it's a hypothesis and the good match that you obtain with experimental observations may confirm this to be a valid constraint for MD simulations of ionic crystals. I'm, more in the world of metals,
Yes.
and I think of MD simulations using a multi-body potential, and you have to fit that to physical properties. But this
Yes.
one here is apparently purely theoretical.
Yes. So first of all, I don't describe it as a constraint. Every atom wants to have its desired valence. But if it doesn't, that means there's a force on that ion in the direction it could move to get its valence.
And
So
there's a
this
coefficient for that.
and there's a coefficient for that. And we fit that to first principles calculations. So that's and if structure after structure, you get the same energies and structures as you would from DFT, then it's basically at the quality of the DFT. And so we've had good success with that. Yes, so we have yielded many experimental observables that we've been able to predict things in advance of experiment. We've been able to rationalize behaviors that experiment is observing indirectly. We can then observe directly at the nanometer or even angstrom scale to provide understanding of experiments. So I think it's an established technique. We are at present working to get this bond valence model as a self-contained module within lamps. There is a famous molecular dynamics code that if you get the code, you get a whole bunch of potentials. We'd like it that people would just get our potentials and then, it would be more convenient. We let other people use them. So it'll be more convenient for other people to use them through the standard distribution of lamps.
This could also be interesting for non-crystalline ionic crystals like materials like glasses.
Yes, you reminded me. The bond valence model is a many-body potential. Because if an atom suppose that titanium has too many bonds, it's going to push all the oxygens away. You see, its bond valence is a sum over all its neighbors. So it's like a pair potential with a sum rule, if you want to say it that way. But that means it's effectively a many-body potential. Yeah, thank you.
Thank you.
Okay, I'll go there and then.
I'll follow up on that.
Is this for recording?
Okay. Yeah, following up on that, were your potentials derived from like a particular composition, or are they extensible to all mixtures?
Oh, this is a wonderful question. The first few that we did were for the most classic ones, lead titanate, lead zirconate, barium titanate. That was a single composition. But in more recent years, we've said, well, zirconium and titanium, people love to alloy these. So we made potentials that were fit to enough compositions. You can vary the zirconium to titanium any way you want. With the lead magnesium niobate, we fit it to 25% lead titanate. But we have now extended it beyond that and said, let's just use it. How bad could it be? And it turns out it gives quite interesting and good results, that the behavior of that particular material, the PMNPT, evolves very rapidly with composition. So we're yielding some interesting new results there. So it is extensible. It's not plug and play everything with everything. So I think there's more development we could do to get closer to that, where you could just use any combination of elements. But we have many in our library already. So I'd be glad to talk to you about that more.
Okay.
Okay, I have two questions.
Yes.
The first one is still about these potentials. Because it's amazing that it works so well, right? And I don't know if you're familiar with the work that David Vanderbilt and his group did many years ago, where they tried to sort of derive effective Hamiltonians, and they needed to put in, the soft mode, and how that's coupled with the strain.
Yes.
And then you eventually they were able eventually to sort of determine the phase diagram of these things. Do you see any link between your model and that sort of approach with effective Hamiltonians?
Yes. Yeah, of course, David's one of my best friends. And so I know this technique extremely well. I would say that the model Hamiltonian, it eliminates some degrees of freedom. Mm-hmm. And so here, because we have all atoms and are doing molecular dynamics, we are, there's some thermodynamics that I think we get that may not be accessible. The model Hamiltonian technique has been very successful. I think it has some of the same issues with extensibility that ours does, that if you say, well, what about a new composition, you'd have to go back and refit again. So I think that's very equivalent. This is dramatically faster than that, maybe 4 orders of magnitude faster. So we did 2 million atoms 10 years ago. We probably could do 1 billion atoms now. We just need to find the right problem where that would actually be necessary. But it's an extremely fast technique. It's at least 2 orders of magnitude faster than the machine learned potentials, which are also wonderful. And I'll talk about them more tomorrow. But this is dramatically more efficient than those as well.
Okay. My second question was about, there is of course a big similarity between magnetic domains, ferromagnetism,
Yes.
ferroelectric. So how much of this theories you developed for the domains and the domain motion and so on could be transported to the magnetic domain, or is the physics somewhere sufficiently different that wouldn't work?
I think there are many ways that I'd like to look for the analogies, but as you know, for a spin, the magnitude of the spin is always fixed. It can reorient, but it cannot go away. Here, the polarization can and does go away at the boundary, you see? So that's totally different. And as a result, you have very sharp boundaries in ferroelectrics. By comparison with most magnetic systems, you have very gentle domain wall boundaries. So I think those are a couple of the differences. But one place where the analogy is very strong is magnetic skyrmions have been established and are a very interesting part of that field. So now researchers, I'm not doing so much of that, but my friends are looking into, to what extent does it help to characterize a phase as a polar skyrmion phase, and would that be a desirable thing to make, and what would its properties be? So I think we are having these kinds of conversations back and forth. And I have some new results for materials that have both electric dipoles and magnetic dipoles. And there's always something new there. If you can find a magnetoelectric coupling, that yields additional functional properties. So I think, yes, we always think about the other side of the fence and the magnetism. Sure.
Sorry, I think we have a lecture, so class here in a few minutes, so we'll need to close the session. But I think we can, those who are interested, maybe if you have time, they can go to the Van Hoon lecture and discuss with you. Is
Sure.
that fine?
Yeah.
Then we need to, yeah. So I think, unfortunately, we need to close it now because there is a lecture scheduled here.
Okay, thank you.
Thank you again.